Okay, cool. Welcome to this talk about MLOps for fairness. I'm Bhakti, and thank you so much for giving me the opportunity to talk about MLOps for fairness. We'll be looking into how to create fairer workflows through some of the toolkits and best practices recommended at Google, mainly Google Research. So let's begin, bias in ML. I'm going to start with a riddle, and I'm going to let you guys answer it. So imagine a father and son are in a horrible car crash that kills the dad. The son is rushed into the hospital just as he's about to go under the knife. The surgeon says, I can't operate, the boy is my son. So can you help me understand what's happening here and how you could go about solving this riddle? Any thoughts here? Yeah, go ahead. That's a very good answer. That is correct. That's one possibility. Any other possibilities? Go ahead. Yes, that is correct. And you'd be surprised that when this study was conducted in Boston University, a lot of folks who describe themselves as feminists forgot that these two could be possibilities of handling this riddle. And that's where bias comes in. It's a classic example. I'm going to show you a quick video of how bias creeps in machine learning. Oops. Gonna try and play that. So I'm going to voice over because of technical difficulties. Imagine you're classifying shoes, and a lot of participants think about shoes in the process, and you ensure that you're trying to classify shoes. You'll pass that into a computer, and then you will basically classify whether it's a male or female shoe or not. And you're training neural networks for this. Now, this is helpful. It basically helps you navigate a lot of handwritten rules, and you can use a neural network for this. And a lot of applications in machine learning, such as a voice recognition, can be handled using ML. In traditional programming, you have a bunch of handwritten rules, but with machine learning, you're training with data. In this example here, you're basically trying to understand if human biases are creeping in this example. And just in the shoe classification example, we will see how bias creeps in. So the interaction bias, now if you're showing users a bunch of shoes, you're more likely to bias them to think about just the shoes that you showed them initially, which could be canvas shoes and heels, and you could be missing out on all the other possible shoes, and this is called latent interaction bias. Now say you're training classifiers, or you're trying to train a classifier to predict scientists. Historically, we have had very few women scientists, so you're going to forget having women in the picture, and that's a classic example of latent bias. Training photos with data, are you selecting representative examples in your data set? So all this encapsulates in understanding bias and understanding how it creeps in technology, and we are constantly trying to improve on that front by taking several measures, which I'll be talking to you about today. So with that, I think I'm gonna talk about MLOps and fairness. So this is your typical ML workflow where you define a problem, and then you collect and prepare data. You train a model, and then you evaluate it, and finally you integrate it and monitor it in your system. And essentially you iterate over the phases so that you are incorporating feedback at different times. And MLOps, which this summit is all about having the right development processes, continuously deploying them through CI/CD building, and gluing all of it together through operations by monitoring and triggering it and putting the right user feedback loops in place. And this is how we see development, deployment, and operations in your typical ML workflow. but bias can creep in a typical ML workflow. So just while you're defining the problem, automation bias or historical bias, like we saw in the case of the examples about scientists, can creep in. And oftentimes it's a matter of correlation and causation that causes you to have these prejudices or bias in the system. And automation bias is overly relying on computers and understanding and thinking that what they know is the best choice forward. So you should be cognizant of these biases in all steps, including definition of problem. And then when you're collecting and preparing data, how are you collecting and preparing your data? Are you sampling the right population? For example, if you are sampling a population where there is no representation of the minority group, you'll just be dealing with a very skewed sample. And then when you're training the model, are you overgeneralizing? Are you underfitting? What's happening? And are you also having experimenter's bias as a trainer of the model, where you're putting in your bias and expecting a certain kind of results to show up? This is me and doing the classic Indian nodding, the nodding of Indian heads, which is very confusing. Whenever I go to different places and I nod like this, people are oftentimes confused whether I'm saying a yes or a no. Why? Because in certain cultures, nodding a head like this means a yes, and nodding a head like that means no. So if I'm designing a gesture recognition system, and if I always say this is a no, it might not scale to all users. And of course, deployment bias. Are we even testing it on the users that we want to serve? Or is there a skew? So it creeps up in all parts of the ML workflow. So now the need for MLOps for fairness is clear. During your development phase, you should start thinking about fairness as a metric. You should have fairness evaluations, have data audits, and also think about how you should incorporate fairness constraints while training models. And deployment, you should have transparency artifacts that communicate to the user what are its limitations, what is the ethical implication of using this model, and of course, using fairness as a business metric through and through. And operations, this is all about monitoring and triggering continuously for bias and skew, and also having right feedback loops in place so that users can communicate and flag things, because not everything is going to be in your data set forever. So having the right feedback loops in place is critical. And of course, compliance with regulatory frameworks in your local areas is also a core part of getting the operations bit right. So we saw the typical ML workflow, and as you want to get better at developing fairer workflows, you should be answering hard questions at every step of your typical ML workflow. So while defining problem, think about whether the system should exist in the first place. Should you have an ML system that detects criminality based on a person's face? Hard no. Who is the intended user, and what are the risks if the ML model goes wrong? And what would success look like? While you're collecting and preparing data, think about how skewed or your distribution is, how it was collected in the first place, and if at all the data was privacy preserving. When you're training the model, you should think about who trained the model and how they trained the model, and if there were any explicit fairness constraints that were put while training the model. And while evaluating, think about what data sets were used to evaluate the model. Was it tested across all user groups and so on? And finally, while you're integrating and monitoring, publish transparency artifacts, ensure that it's complying to local rules and so on, and observe for decay and drift. So I'm going to present a couple of recommendations from Google. So we have a lot of tools that you can check out for getting some of these right. Some of these are open source, some of these are also present in our cloud ecosystem. Today I'll be covering some of these here. So let's look at defining the problem. So I'm going to talk about these two pieces here. So Google's approach to AI principles has been to adhere to these principles before you even start training your ML model, thinking if the problem is going to be socially beneficial, and as you're going through, it should not enforce bias, it should be safe, and throughout our development phases, we iteratively try to become better at these AI principles. And of course, you should not be pursuing AI where it's likely to cause harms in terms of weapons or surveillance and so on. And to guide you through this, we have the People Plus AI guidebook. It'll take you through various case studies and explorables where you can understand how you should be defining user success, how you should be thinking about setting up feedback and control in your AI problems, and how you should handle errors when things go wrong gracefully. So I'm going to take you through an example. A core part of getting this piece right is just understanding what fairness is. We don't have time to discuss a lot of fairness issues, but I'm going to take you through some fairness goals and how they would look like. So imagine we have two groups, blue and orange. We are giving them loans, and essentially a successful loan would make us $300, unsuccessful loan would cost us $700. Everybody has a score between 0 and 100. Now when you're giving loans, you have several definitions of fairness. And as a model owner, you need to think about which definition of fairness you want to go for, because sometimes these fairness definitions do contradict also. So think about what success looks like. So now just for a loan example case, we could be thinking about just being unaware. I don't care whether you're blue or orange. This is my threshold. If your credit score is above 55, you get a loan. You could say that this would make the bank this much profit. And then you could talk about demographic parity, which essentially involves saying, I'm going to ensure that the positive rate for both the groups is the same, and that has a different impact on the business metric altogether. Now you could talk about equality of opportunity, where you could say that I want my true positive rate for both the groups to be the same. And that would have different implications on your business metric as well. So once you figure out what your fairness goal is, which is a very important piece, you should also think about who the users are. So this is an example of project a portrait. So this basically is the portrait filter that you see on Pixel phones. So once you have your fairness goal in mind, that you want to do well for these groups on these metrics, you should think about who the users are. And especially for this one, we used the monk skin tone. We thought about our users in terms of race, gender, age, and skin tone, and so on. And you can read more about the case study here as well. Thinking about users is important. So that's the defined problem, very socio-technical, I agree. But for the technical crowd here, I'm going to show you more tools that you can use once you have your define the problem piece set. Next one is know your data. So this is another tool you can use. It lets you explore your data. And it lets you see how different features are spread across in your data set. And you can also use some of the cloud vision signals. So these are features that are not present in your data set, but we'll look them up for you and we'll tell you, oh, is there a face in this data set? Or was the data captured during night, or was it captured with less sharpness, and so on. It helps. And then most important part, you can also understand relations between the features. Are you seeing a correlation between someone wearing a hat and someone smiling? Because your model could end up just using wearing a hat as a proxy for smiling. So what to look for with KYD? Skewed samples. For example, here you're seeing the words attractive correlate very often with females in a textual data set, and handsome with male, but you can see the kind of correlation, and you might be dealing with proxies here. Tainted examples, sometimes there are incorrectly labeled samples, and you can use other signals to basically understand if you've missed out on labels. For example, if you're dealing with a driving data set, you forgot to label someone as a human, there are some signals that you can use to essentially look for tainted labels also. And then proxies, like I mentioned. This is another textual data set, and you can see that the active words are often correlated with the young audience, like dancing and jumping and swimming, and then the older population does not have this correlation. So you can use point-wise mutual information, which is inbuilt in KYD, to understand these correlations. And finally, most important, sample size disparity. If you're doing a data set on faces, do you have more examples of men than women? Do you have more examples of people wearing hats? Or basically, how are your features distributed? Is there a skew? So that was about data. And then once you have the data, you know the problems, you can remediate parts of it, or you could collect new data, or you could also force your model to learn things in a certain way, keeping your data constant. So we'll look at some of the toolkits here. So model remediation techniques could be data remediation, where you oversample a few things, or you generate synthetic data, or you adjust the sampling rates or weights of examples, essentially, to compensate for the data issues. It could be training time modeling techniques, where you add an explicit constraint to the way you're training your model, or potentially by adding a regularizer and so on. Or it could also involve post-training, which essentially means you modify the output in a certain way, give confidence scores, calibrate it in a certain way, just so that you know you're handling things with transparency. So one toolkit in the TensorFlow model remediation toolkit is MinDiff. Imagine you're trying to train a classifier, you have seen very bad performance in the majority and the minority groups, and you essentially want to equalize the two distributions. So you can add this MinDiff loss to your model's training along with your main loss, and you will see that it does well in normalizing or equalizing the distributions of the two rates. This is helpful if your goal is equality of opportunity. And then there's also TensorFlow constraint optimization. So oftentimes these fairness goals can be written as explicit fairness constraints. Imagine you're trying to train a classifier where you're trying to predict if people are smiling or not in a picture. And you see that you're doing very well for the you're doing very well for the younger population, not so for the older population. You add these constraints to your model as you're training it, and you can see that basically the performance, the false positive rate, which is the fairness goal here, is improving post adding these constraints. Or you're training a toxicity classifier for text, and you want to ensure that each one of these sentences is getting the same score of toxicity, and that's not happening. So essentially you can, and this is the classic example of counterfactual fairness, where you look at individuals now and not groups, and you're trying to ensure that each one of these are treated similarly. So you can add a counterfactual loss to your model, which basically penalizes the model for treating each of these sentences differently, and you will see that after training it with counterfactual loss, the toxicity scores across these groups are more homogenized. And finally, once you train, you need to evaluate the model. You can use the fairness indicators toolkit. So what this lets you do is it lets you do sliced evaluations across groups, and it also lets you compare results between groups and also the overall groups. Most important thing, it gives you confidence intervals. When you're dealing with fairness, data is often sparse. You will not have enough examples from all groups. It's important to put together some bootstrapping process that gives you an estimate of how confident you are on these metrics, and that's built under the hood for fairness indicators. There's also the what if tool that you can use. So basically you take a data point, tweak a couple of values, and see if the decision flips. Now that's helpful to understand if your model is basically over-indexing on a couple of features, or if it's not adhering to counterfactual fairness. There's a language interpretability tool. In case you're designing a sentiment classifier, just adding the word waiter and the word waitress is enough to flip the decision of the model. This helps you debug and deep dive into what's going wrong with your model, and especially helpful if you're dealing with a lot of textual data. And finally, once you're done evaluation, you should monitor and you should publish the transparency artifacts. So model monitoring, a lot of talks in this summit have been about model monitoring. As you are monitoring features or predictions, it's important to look for biases, and if it's adhering to the fairness goals you had set in your previous, in the previous stage of the ML life cycle. So it's very important to use tools, any tools, but monitor the models, and you can use the Google Cloud's model monitoring for this, or any other tool for that matter, but monitoring is important. And then transparency is important for everybody. It's not just for model developers alone, engineers or data scientists. It's important for the users. It's important for the people who oversee the models, including the government. And that's why you should publish model cards and data cards. So model cards here is all about putting down the limitations of the model, talking about the intended use cases of the model, and understanding how it was trained, on what data it was trained, and just publishing this so that people who use the models know what to expect from your ML system. So in all, you have a ton of resources here that you can use to get your ML lifecycle right. These are some recommendations from Google, but of course you can extrapolate them into your ecosystem. And with that, I would like to thank you for your time and happy to take more questions. Thank you.